Was the Big Bang just a white hole? A cosmic question that might reshape everything we thought we knew about our universe's beginning. Picture this. What if that explosive moment 13.8 billion years ago wasn't actually the start of everything, but rather the dramatic exit from something else entirely? What if our cosmos burst forth not from nothingness, but from the interior of a white hole, connected through the fabric of space-time to a collapsing black hole in another universe? The story we've long been told feels complete and elegant. The Big Bang theory has been remarkably successful, explaining why galaxies rush away from us, predicting that faint afterglow we call the cosmic microwave background, and even telling us how the lightest elements formed in those first crucial minutes. Yet beneath this triumph lie nagging puzzles that refuse to disappear. Take the horizon problem, for instance. When we gaze across the universe, regions separated by billions of light years appear eerily similar in temperature and density. But there wasn't enough time since the Big Bang for light or anything else to travel between them and smooth things out. It's as if two strangers on opposite sides of the world somehow ended up wearing identical outfits without ever communicating. Then there's the flatness problem. The shape of space-time appears perfectly balanced, not curved inward like a sphere or outward like a saddle, but flat, and not just approximately flat, but so precisely flat that even tiny differences in the early universe should have grown into enormous ones by now. This level of fine-tuning seems almost supernatural, as though the cosmos was carefully calibrated from the very beginning. To patch these holes, scientists introduced cosmic inflation in the 1980s. This theory proposes that just after the Big Bang, the universe expanded faster than light for a tiny fraction of a second, smoothing out irregularities and flattening space. While elegant, inflation brings its own mysteries. Where did this sudden expansion come from? What started it, and why did it stop so perfectly? Moreover, inflation depends on fields and particles we've never directly observed. Today, the invisible components of our universe, dark matter and dark energy, make up about 95% of everything that exists. We've built our model on the thin slice we can actually see. This has led some researchers to ask a bold question. What if we're missing something fundamental? What if the Big Bang, helpful as it's been, is only part of a much larger story? At the heart of this mystery lies the initial singularity, that theoretical point where the entire universe was compressed into something with zero volume, but infinite density. It's not just that things were crowded or hot, it's that space itself had no size, and time had no duration. When physicists encounter infinity in their equations, it's usually a red flag. It means the math has broken down, and the rules that guide us have fallen apart. General relativity predicts this singularity, but it also tells us we can't actually describe what happens there. The very framework of the theory becomes unusable. It's like a warning sign saying, "Abandon hope, all mathematics who enter here." This is where white holes enter the conversation. They're the theoretical mirror images of black holes, regions where nothing can enter but energy and matter can leave. While we've never seen one, they emerge naturally from the same equations that gave us black holes. In the extended mathematics of spacetime, every black hole comes paired with a white hole, connected through what Einstein and Nathan Rosen called a bridge. Imagine standing near a white hole if such a thing could exist. You would see matter and light streaming out from an invisible surface. The energy would come from a point in the past that can't be reached. The moment anything tries to get close, it's pushed away by the structure of space-time itself. It's like a cosmic fountain, a place where matter appears, flows out, and then is gone. Now here's where things get truly fascinating. What if the Big Bang wasn't the beginning of everything, but the explosive emergence from a white hole? What if our entire universe is the expanding interior of such an object, forever ejecting matter and energy outward, from that initial moment, this idea helps address some of the Big Bang's most troubling aspects. Instead of everything coming from an impossible singularity, our universe could have emerged from the interior of a black hole in another cosmos. When that black hole reached its ultimate fate, quantum effects might have caused it to bounce, not collapse further, creating a white hole that gave birth to our reality. In this picture, the Big Bang becomes a transition, not a beginning. Our universe didn't come from nothing, it came from something else. The uniformity we see across the cosmos might reflect the interior structure of that parent black hole. The flatness of space might be a natural consequence of the white hole geometry. Some physicists have explored this through modified theories of gravity that include something called torsion. In these models, when matter gets extremely dense, the spin of particles interacts with the twisting of spacetime to produce a repulsive force. This force can halt collapse before a singularity forms and drive a new expansion. What follows looks very much like a white hole, matter emerging not from a mathematical impossibility, but from an extreme but finite compression that then explodes outward. Other researchers have taken a different approach, using classical shockwave theory to describe the Big Bang. In this view, our universe's beginning wasn't a singularity, but a sharp boundary, a cosmic shock front moving through a pre-existing spacetime. Inside the shockwave, space is filled with expanding matter and radiation. Outside, there's a vacuum or empty geometry. The Big Bang becomes not the birth of time, but a transformation within it. There's even the possibility that our universe budded off from another through quantum tunneling. Just as particles can tunnel through barriers in quantum mechanics, entire patches of spacetime might tunnel out from their parent universe. If a region exists in what physicists call a false vacuum, it could suddenly decay, creating a bubble that becomes its own sealed-off cosmos. The observational consequences of a white hole origin could be profound. The cosmic microwave background, that faint afterglow from the early universe, might carry subtle signatures of this explosive birth, strange alignments or temperature patterns that don't quite fit. Standard models could be echoes of the white hole geometry. Future gravitational wave detectors might catch primordial ripples in spacetime that bear the fingerprints of this violent emergence. Unlike the smooth hum expected from inflation, a white hole birth might produce sharp spikes or directional biases in the gravitational wave background. Even the abundances of light elements formed in the universe's first few minutes could tell us about white hole conditions. The delicate nuclear reactions that created hydrogen, helium, and lithium are incredibly sensitive to how fast space expanded and cooled. Any deviation from standard Big Bang nuclear synthesis might hint at a more exotic origin. The search for white holes themselves remains one of astronomy's great challenges. If they exist, they might appear as brief, intense bursts of energy, gamma-ray bursts, or fast radio bursts with no clear source. They could be the cause of mysterious X-ray emissions from dark regions of space, or they might produce gravitational waves with unique signatures that future detectors could identify. Yet white holes face serious theoretical hurdles. They seem to violate the second law of thermodynamics, which says entropy always increases. How can a region of space eject organized matter without prior input? They also appear unstable. Any small disturbance should cause them to collapse or disappear almost instantly. Some physicists propose solutions involving exotic matter with negative energy density, the kind of substance that might exist in quantum field fluctuations, but would be nearly impossible to gather in large amounts. Others suggest that white holes might only be possible in the quantum realm, tiny unstable objects that blink in and out of existence in the foam of spacetime itself. The connection to wormholes adds another layer of intrigue. If traversable wormholes could exist, their exit points would have all the properties of white holes. They would eject matter, repel objects, and nothing could enter from the outside. This raises the possibility that our universe might be connected to others through these cosmic tunnels, with matter falling into black holes in one reality and emerging from white holes in another. In the realm of quantum gravity, where general relativity meets quantum mechanics, white holes become even more mysterious. String theory struggles to accommodate them, while loop quantum gravity suggests they might naturally emerge from the quantum bounce of collapsing black holes. These are the frontiers where our understanding breaks down, and new physics might emerge. The particle physics implications are equally mind-bending. If the universe emerged from a white hole, the entire stage for how matter formed, how the fundamental forces behaved, and why we see more matter than antimatter could be radically different. Instead of a gradual unfolding from thermal equilibrium, we might have witnessed a violent, asymmetric explosion that naturally favoured matter over antimatter. The topology of our universe, its overall shape and connectivity, might also bear the imprint of this white hole origin. If space emerged from such a bounded source, it might naturally be closed and finite, like the surface of a sphere, but in higher dimensions. Or it might have a more exotic structure, twisted and connected in ways that could leave observable signatures in the cosmic microwave background. As we stand at this crossroads of observation and theory, the white hole hypothesis represents more than just an alternative to the Big Bang. It embodies our deepest questions about existence itself. Where did everything come from? What came before? Are we alone, or part of a vast network of connected universes? The universe we observe expanding around us, filled with galaxies and stars, and the raw materials of life, might be the interior of something far grander than we ever imagined. Every photon of starlight, every atom in our bodies, every breath we take might be part of an ongoing explosion that began not with the creation of everything, but with the dramatic exit from somewhere else entirely. Whether white holes are real or remain forever in the realm of mathematical possibility, they remind us that the cosmos is far stranger and more wonderful than our everyday experience suggests. They challenge us to think beyond the boundaries of the familiar, to imagine realities where time can reverse, where universes give birth to other universes, and where the ultimate nature of existence might be found, not in beginnings, but in transformations. The search continues in the equations of theorists and the observations of astronomers, in the data streaming back from space telescopes and the ripples detected by gravitational wave observatories. Somewhere in that vast collection of information might lie the clues that tell us whether our universe truly began with a bang, or whether it emerged, fully formed and expanding, from the white-hot interior of something even more magnificent. Until then, we're left with wonder, that most human of emotions, as we contemplate our place in a cosmos that might be just one chapter in an infinite story of creation, destruction, and rebirth. The Big Bang gave us a beginning, but white holes offer us something perhaps even more profound, the possibility that there was never really a beginning at all, just an eternal dance of matter and energy, space and time, flowing from one reality to the next, in an endless cosmic symphony. The dance of quantum fields, when the universe whispers in mathematics. We've explored the wild possibility that our cosmic birth was not a beginning from nothing, but an explosive emergence from elsewhere. We've seen how white holes might serve as cosmic fountains, ejecting matter and energy from hidden realms beyond our reach. But now, we must venture deeper into the quantum realm, where the very fabric of reality becomes uncertain, where particles flicker in and out of existence, and where the classical certainty of Einstein's equations gives way to the probabilistic whispers of quantum mechanics. In the standard view of cosmology, quantum fields play a supporting role. They create the tiny fluctuations that seed galaxies. They drive inflation through mysterious scalar fields, and they govern the behavior of matter at the smallest scales. But what if quantum fields are not just actors on the cosmic stage? What if they are the stage itself, the fundamental substrate from which space, time, and perhaps even white holes emerge? This is where our story takes a fascinating turn, because quantum field theory suggests something remarkable about the vacuum of space. What we call empty space, the void between galaxies, is not truly empty at all. It seethes with activity, filled with quantum fields that fluctuate wildly at the smallest scales. These fluctuations are not just theoretical curiosities. They have real, measurable effects. They create the Casimir force between metal plates, they contribute to the anomalous magnetic moment of the electron, and they may even be responsible for the mysterious dark energy that drives cosmic acceleration. But here's where things get truly strange. In quantum field theory, the vacuum is not unique. There can be multiple vacuum states, each with different properties, different energy levels, and different rules for how particles behave. Some of these vacuums are stable, like the bottom of a deep valley. Others are metastable, like a boulder balanced precariously on a hillside. And if our universe exists in a false vacuum, a temporary state of apparent stability, then it could undergo a sudden transition to a lower energy state. Such a transition would not be gentle. It would create a bubble of true vacuum that expands outward at the speed of light, rewriting the laws of physics as it goes. From the outside, this bubble would look exactly like a white hole. Matter and energy would pour out of it, but nothing could enter. The boundary between the old vacuum and the new would act as an event horizon in reverse, allowing only outward flow. This opens up a remarkable possibility. What if our Big Bang was not the creation of space and time from nothing, but a quantum phase transition? What if our entire universe is the interior of a bubble that nucleated in some larger metastable vacuum? The mathematics of bubble nucleation, developed by Sidney Coleman and others in the 1980s, provides a framework for understanding how such transitions might occur. In this picture, the before our Big Bang was not temporal but spatial. There was a parent vacuum, perhaps infinite in extent, filled with quantum fields in a metastable state. Through quantum tunneling, a rare but inevitable process, a small region underwent a phase transition. This created a bubble of true vacuum that began expanding outward. Inside this bubble, the field configuration was different. The particle masses were different. Perhaps even the dimensionality of space was different. From our perspective, trapped inside this expanding bubble, we would see an expanding universe filled with matter and radiation. We would measure a cosmic microwave background, observe the recession of galaxies, and detect the abundance of light elements created in the first few minutes. All the standard evidence for the Big Bang would be there, but the interpretation would be radically different. We would not be witnesses to the birth of everything, but inhabitants of a cosmic bubble, one of perhaps infinitely many such bubbles scattered throughout a vast metastable sea. This bubble universe scenario has profound implications for our understanding of physics. It suggests that the constants of nature, the particle masses, the strength of forces, might not be fundamental at all. They might simply be the low-energy properties of whatever vacuum state we happen to inhabit. In other bubbles, in other pocket universes, these constants could be completely different. Some bubbles might have no electromagnetic force, others might have extra spatial dimensions, and still others might be filled with exotic forms of matter we can't even imagine. The quantum field picture also provides a natural explanation for some of the puzzles that plague standard cosmology. Why is the universe so flat? Because the bubble wall naturally creates a flat geometry as it expands. Why is it so uniform? Because the interior of the bubble starts from a single, well-defined quantum state. Why does it contain so much matter relative to antimatter? Because the phase transition itself breaks certain symmetries, creating a natural imbalance. But perhaps most intriguingly, the quantum field approach suggests that white holes might not be exotic, impossible objects after all. They might be the natural consequence of vacuum decay, as common and inevitable as radioactive decay or quantum tunneling. Every metastable vacuum will eventually decay, creating expanding bubbles of true vacuum. From the inside, each bubble looks like a Big Bang. From the outside, each bubble looks like a white hole. This perspective transforms our understanding of cosmic origins. Instead of asking how something came from nothing, we ask how one kind of something transformed into another. Instead of seeking a first cause, we explore the dynamics of phase transitions. Instead of imagining a unique beginning, we envision an eternal process of bubble nucleation, each event creating a new pocket universe with its own physics, its own history, and its own observers wondering about their origins. The mathematics of this scenario are still being developed. Quantum field theory in curved space-time is notoriously difficult, and the dynamics of bubble walls in expanding space involve complex interactions between geometry and matter. But the basic framework is sound, grounded in well-tested principles of quantum mechanics and general relativity. Moreover, this picture makes testable predictions. The cosmic microwave background should carry subtle imprints of the bubble wall, specific patterns in temperature and polarization that differ from those predicted by inflation. The spectrum of primordial gravitational waves should show characteristic features related to the phase transition. The abundance of primordial black holes, if they exist, should reflect the turbulent dynamics of vacuum decay rather than the smooth evolution of an inflating field. As we peer deeper into the cosmic microwave background with ever more sensitive instruments, as we detect gravitational waves from the earliest moments of cosmic history, we may finally be able to test these ideas. We may discover that our universe is indeed the interior of a quantum bubble, born not from nothing but from a phase transition in a vast, eternal multiverse of metastable vacuum. In this view, white holes are not violations of thermodynamics or exotic solutions to Einstein's equations. They are the natural consequence of quantum field dynamics, the inevitable result of vacuum instability. They are not objects that exist in space, but pockets of space itself, expanding regions of true vacuum carving out new territories in the landscape of possibility. And if this is true, then our universe is not alone. Somewhere in the vast expanse of the parent vacuum, other bubbles are nucleating, other big bangs are beginning, other white holes are erupting into existence. Each one creates a new cosmos, a new stage for matter and energy to dance their ancient choreography. Each one is a fresh start, a clean slate, a new chapter in the endless story of existence. We may never be able to communicate with these other bubbles, these parallel universes born from quantum phase transitions. The bubble walls expand at light speed, creating causal horizons that separate each universe from its neighbours. But we can take comfort in knowing that we are not alone, that our cosmos is one note in a vast symphony, one bubble in an infinite sea of possibility. The dance of quantum fields continues, eternal and ever-changing, creating and destroying, transforming nothing into something and something into something else. In this dance, white holes are not exotic exceptions but natural expressions of the universe's deepest creativity, the quantum mechanical tendency to explore every possibility, to fill every vacuum, to turn potential into reality. Perhaps this is the true meaning of our cosmic origins, not a miracle of creation from nothing, but a manifestation of the universe's inexhaustible capacity for transformation, its endless ability to surprise us with new forms of beauty, new patterns of complexity, new ways of being. In the quantum realm, where uncertainty reigns and possibilities proliferate, white holes may be as natural as the morning sunrise, as inevitable as the turning of the seasons, as beautiful as the dance of particles in the void. Building on the intricate tapestry we've woven through quantum fields, vacuum transitions, and cosmic phase changes, we now arrive at perhaps the most profound question in our exploration. If our universe did emerge from a white hole, what would this mean for the deeper nature of reality itself? The implications stretch far beyond cosmology into the very foundations of existence. Consider this. If the Big Bang was indeed a white hole eruption, then our universe becomes not a unique creation event, but part of an ongoing cosmic metabolism. Every black hole in our cosmos could be a nursery for future universes, each one inheriting modified physical constants and laws through a process of cosmic natural selection. This perspective transforms our understanding of time in radical ways. Rather than time beginning at t=0, we're looking at time as a flowing river that passes through cosmic waterfalls. The white hole represents not a beginning, but a transition point where the flow of causality changes direction. Information and energy from a previous cosmic epoch would cascade through this temporal bottleneck, emerging transformed but not destroyed. The quantum mechanical implications are equally staggering. If our universe emerged from a white hole, then the wave function of our entire cosmos carries within it the quantum signature of whatever came before. This means that the fundamental randomness we observe in quantum mechanics might not be truly random at all, but rather the scrambled echo of deterministic processes from a parent universe. From this lens, the fine-tuning problem that has puzzled cosmologists for decades begins to dissolve. The precise values of physical constants that allow stars, galaxies, and life to exist wouldn't be miraculous coincidences or evidence of multiple universes. Instead, they would be the naturally selected outcomes of countless generations of cosmic reproduction, where universes that produce stable black holes create more offspring. The white hole hypothesis also offers a stunning resolution to the information paradox that has haunted black hole physics. If black holes don't destroy information, but rather process it for transmission to baby universes, then the fundamental reversibility of quantum mechanics remains intact. The information doesn't disappear, it gets recycled into new cosmic structures. This model suggests that consciousness itself might be part of a much grander cosmic story. If universes evolve and reproduce, and if the emergence of complex information processing systems, like brains, is a natural outcome of cosmic evolution, then consciousness becomes not an accident, but an inevitable feature of mature universes. We wouldn't just be observers of the cosmos, we'd be participants in its reproductive cycle. The implications for the search for extraterrestrial intelligence become profound under this framework. Advanced civilizations wouldn't just be rare occurrences in isolated cosmic bubbles. They would be integral components of cosmic evolution, potentially capable of influencing the formation of black holes and thereby participating in the creation of future universes. Even our understanding of death and endings transforms under this perspective. Just as individual black holes might give birth to new universes, the death of our own cosmic epoch wouldn't represent true ending, but cosmic metamorphosis. The heat death of our universe, that far future, when all stars have burned out and only black holes remain, becomes not a finale, but a preparation phase for cosmic reproduction. The white hole origin story also reframes our relationship with the unknown. The dark matter and dark energy that comprise 95% of our universe might be the processed remnants of structures from the parent cosmos, carrying within their invisible architecture the blueprints for cosmic organization that we're only beginning to decipher. This perspective suggests that the deepest questions of existence, why something rather than nothing, why these laws rather than others, why consciousness, might have answers that transcend any single universe. We become part of an infinite cosmic family tree, each branch exploring different possibilities, each universe a unique experiment in the space of all possible realities. The white hole hypothesis doesn't just change how we think about our cosmic origins, it revolutionizes our understanding of purpose and meaning in an apparently vast and indifferent universe. We're not accidental arrangements of atoms in a purposeless void. We're active participants in a cosmic evolutionary process that spans scales from quantum to universal, from microseconds to geological epochs. In this view, every choice we make, every structure we build, every piece of knowledge we discover contributes to the information content that our universe will pass on to its descendants. We become co-creators in the ongoing cosmic story, our consciousness and creativity helping to determine what kinds of universes will emerge from the black holes our cosmos creates. The white hole origin hypothesis transforms cosmology from a study of how things began into an exploration of how things continue, how information and complexity flow through the cascade of cosmic generations, and how consciousness and intelligence emerge as natural expressions of the universe's creative potential. Whether this vision proves correct or not, it demonstrates how profoundly our understanding of existence can shift when we dare to question our most basic assumptions about beginnings, endings, and the nature of time itself. The universe may be far stranger and far more purposeful than we ever imagined. Now, diving deeper into this white hole hypothesis, we need to confront one of the most profound puzzles in all of physics: the nature of vacuum itself. You see, when we talk about a white hole spewing forth matter and energy, we're really asking where that energy comes from in the first place. And this brings us face to face with one of the most startling discoveries of modern physics. The quantum vacuum is not empty. In quantum field theory, what we call empty space is actually a seething cauldron of activity. Virtual particles pop in and out of existence. Energy fluctuates wildly at the smallest scales. The Heisenberg uncertainty principle ensures that even in the deepest vacuum, energy and time are locked in a cosmic dance of borrowing and repayment. This isn't just theoretical speculation. We've measured these effects in laboratories through phenomena like the Casimir effect, where two metal plates placed incredibly close together experience a measurable force from the quantum vacuum. But here's where things get truly extraordinary. Some theories suggest that what we call a false vacuum could undergo a phase transition, a kind of cosmic bubble nucleation that creates entirely new regions of space-time. Picture it like this. Imagine our universe exists in what appears to be the ground state of energy, but it's actually sitting on a ledge. Below this ledge lies the true vacuum, a state of even lower energy. If a region of space tunnels down to this true vacuum state, it creates a bubble that expands at the speed of light. And inside this bubble, the laws of physics themselves might be different. This process could manifest as what appears to be a white hole. The energy difference between the false vacuum and true vacuum gets converted into matter and radiation, creating an explosive outflow that looks exactly like what we observe in our expanding universe. The beautiful thing about this mechanism is that it doesn't violate conservation of energy. The total energy of the system remains zero. It's just redistributed from the vacuum itself into the matter and radiation we see around us. Now, this leads us to an even more startling possibility: cosmic reproduction. If black holes in our universe can collapse down to conditions where quantum effects dominate, they might undergo their own vacuum transitions. Instead of forming a classical singularity, the extreme curvature of spacetime could trigger a phase transition that nucleates a new bubble of spacetime, effectively giving birth to a baby universe through what appears from the outside as a white hole. This isn't just wild speculation. Loop quantum gravity, one of our leading theories for quantum gravity, suggests that when matter collapses to the Planck density, quantum effects create a repulsive force that prevents the formation of a true singularity. Instead, the matter bounces back, potentially creating a white hole that expands into a new region of space-time. If this is true, then our universe might not be unique. It could be one node in a vast cosmic network, where universes give birth to other universes through black hole-white hole transitions. Each new universe inherits slightly modified physical constants from its parent, leading to a kind of cosmological natural selection, where universes that are good at producing black holes end up having more offspring. The implications are staggering. It means the Big Bang wasn't the beginning of everything, but rather a transition point, a cosmic birth canal, connecting our universe to whatever came before. The cosmic microwave background, that faint afterglow we see in every direction, might not just be the echo of our universe's birth, but the stretched and cooled radiation from the death throes of a previous cosmos. This perspective completely reframes our understanding of existence itself. We're not just observers in a universe that somehow sprang from nothing. We're participants in an ongoing process of cosmic evolution that stretches back through an infinite chain of parent universes, each one contributing to the next through the fundamental processes of collapse, transition, and rebirth. And here's the truly mind-bending part. If this process has been going on forever, then every black hole in our universe is potentially pregnant with future cosmos. Every star that collapses, every galactic center that devours matter, might be nurturing the seeds of universes yet to come. In this view, the universe isn't winding down toward heat death. It's perpetually creating new arenas for complexity, consciousness, and cosmic evolution. The search for evidence of this cosmic reproduction continues. We look for anomalies in the cosmic microwave background that might hint at pre-Big Bang physics. We study the behavior of black holes for signs of information preservation that might suggest they're not endpoints but transition points. We develop new theories of quantum gravity that might explain how space-time itself can undergo phase transitions. But perhaps most importantly, this white hole hypothesis reminds us that even our most fundamental assumptions about reality might need revision. The idea that the universe began from nothing, that space and time themselves were created in a singular moment, might be just one chapter in a much grander story of cosmic evolution, connection, and endless creativity. Now, as we've wandered through the puzzling terrain of cosmic origins and theoretical physics, we arrive at perhaps one of the most profound questions in modern cosmology. If our universe didn't emerge from a traditional Big Bang singularity, if it wasn't born from absolute nothingness through mysterious inflation, then what alternative could possibly account for the breathtaking complexity and fine-tuned precision we observe around us? The answer may lie in one of the most exotic predictions of Einstein's equations, something so strange that even seasoned physicists struggle to wrap their minds around it. Picture, if you will, the perfect opposite of a black hole. Where a black hole devours everything that crosses its event horizon, never allowing escape, imagine instead a cosmic boundary that permits only outward flow. Nothing can enter, but everything can leave. This is a white hole, and it represents far more than just mathematical curiosity. It might be the key to understanding how universes are born. The concept emerges naturally from the same equations that gave us black holes. Yet white holes seem to violate our everyday understanding of how time and causality work. They appear to eject matter and energy from a single point, expanding outward like a cosmic fountain that runs in reverse time. But here's where things become truly fascinating. When you examine the mathematics of a white hole explosion, when you trace the geometry of space-time around such an object, something remarkable emerges. The interior of a white hole, the region where matter and energy flow outward from a central point, bears an uncanny resemblance to our expanding universe. Think about what we actually observe when we look into deep space. Galaxies rushing away from us in all directions as if flung outward from some primordial explosion. The cosmic microwave background, that faint afterglow of creation, streaming toward us from every corner of the sky. The universe appears to be in a state of perpetual expansion, with everything moving away from everything else, following patterns that suggest a single, violent birth event in the distant past. This is precisely what you would expect to see if you were living inside a white hole. The mathematics of general relativity suggest that the interior of such an object would experience exactly this kind of expansion. Space itself would stretch, carrying matter and radiation outward, creating the illusion of a universe born from a singular point, when in reality it emerged from a more complex geometric structure. But white holes offer something even more intriguing than just an alternative description of cosmic expansion. They provide a potential solution to some of the deepest mysteries that have plagued cosmology for decades. Consider the horizon problem, for instance. How did regions of space that should never have been in causal contact end up with identical temperatures? In a white hole scenario, all of this matter and energy originates from the same source, from the same interior region, naturally explaining the observed uniformity without requiring exotic inflation fields. The flatness problem, too, finds a more elegant resolution. Our universe appears to be balanced on a knife's edge between expansion and collapse, with a geometry so precisely tuned that even tiny deviations early on should have grown into enormous distortions by now. But if space itself emerged from a white hole, if the geometry was shaped by the outflow from such an object, then this apparent fine-tuning might not be coincidental at all. It could be a natural consequence of the white hole's structure. Even more compelling is the possibility that white holes could be connected to black holes through Einstein-Rosen bridges, those theoretical tunnels through space-time that we call wormholes. If such connections exist, then our universe might not have emerged from nothing at all. Instead, it could be the product of matter and energy that fell into a black hole in some parent universe, travelled through the bridge, and erupted outward through a white hole to create our cosmic home. This paints a picture of universe creation that is both more violent and more gentle than traditional Big Bang cosmology. More violent because it involves the explosive outflow from an exotic object operating under extreme gravitational conditions. More gentle because it avoids the mathematical nightmare of infinite density and temperature that plague singularity-based models. Instead of everything emerging from a point of zero size, our universe could have emerged from a finite, though incredibly dense region, shaped by the curved geometry of spacetime itself. The implications extend far beyond cosmology. If white holes can serve as cosmic birth canals, connecting one universe to another through the interior of black holes, then we might be part of an infinite network of interconnected realities. Each black hole in our universe could potentially give birth to new universes through white hole eruptions. Each galaxy that collapses into a supermassive black hole could be seeding the creation of entire cosmic realms, populated with their own stars, planets, and perhaps even life. This vision transforms black holes from cosmic graveyards into cosmic nurseries. Instead of being the final destination for matter and energy, they become way stations in an eternal cycle of death and rebirth. Matter falls in, travels through impossible geometries, and emerges in new spaces and times, carrying the seeds of future evolution. Such a model also addresses one of the most troubling aspects of traditional cosmology, the question of what came before. If the Big Bang was truly the beginning of time, then asking what preceded it becomes meaningless. But if our universe emerged from a white hole connected to a pre-existing black hole, then time itself might stretch back indefinitely through an endless chain of cosmic generations. Each universe would give birth to others, which would in turn spawn their own offspring, creating a family tree of realities that extends infinitely into the past and future. The energy requirements for such a process are staggering, yet they might be naturally satisfied by the physics of gravitational collapse. When matter falls into a black hole, it doesn't simply disappear. General relativity suggests that it might be compressed and transformed, potentially emerging elsewhere with all its energy intact. The conservation laws that govern our universe would ensure that nothing is lost, only relocated and restructured according to the strange rules of curved spacetime. This brings us to one of the most profound questions in all of science: the nature of existence itself. If universes can reproduce through black hole-white hole connections, if the cosmos is not a single isolated bubble, but part of an infinite network of interconnected realities, then what does this mean for our understanding of purpose, meaning, and our place in the grand scheme of things? Perhaps we are not the products of a singular, unrepeatable event, but participants in an ongoing process of cosmic evolution that has been unfolding for eternity. Perhaps the complexity and beauty we see around us, from the spiral arms of galaxies to the intricate chemistry of life, represent not a miraculous accident, but the inevitable outcome of a universe that has been refining and improving itself through countless generations. The mathematical foundations for this vision already exist, hidden within the equations that Einstein wrote down more than a century ago. The challenge now is to develop these ideas further, to make predictions that can be tested against observation, and to explore the full implications of a cosmos where universes reproduce like living organisms. Recent advances in gravitational wave astronomy, high-energy particle physics, and precision cosmology are providing new tools for probing these exotic possibilities. We may soon have the technology to detect the signatures of white hole explosions, to measure the subtle distortions in spacetime that such events would create, and to trace the cosmic history all the way back to its most fundamental origins. Whether or not our universe actually emerged from a white hole, the very possibility forces us to reconsider our most basic assumptions about reality. It reminds us that the cosmos might be far stranger, far more interconnected, and far more creative than we ever dared imagine. And it suggests that the story of existence, rather than having a clear beginning and end, might be an eternal adventure that spans infinite time and infinite space, with each of us playing a small but meaningful role in an unfolding drama of cosmic proportions. The mathematics behind these connections runs even deeper than we might first imagine. When physicists like Abhay Ashtekar and his colleagues began working through the equations of loop quantum gravity in the early 2000s, they weren't just trying to smooth out singularities or avoid mathematical infinities. They were uncovering something far more profound about the nature of space and time itself. You see, in loop quantum gravity, space isn't the smooth, continuous fabric that Einstein envisioned. Instead, it's woven from discrete threads, tiny loops of quantum geometry that exist at the Planck scale. These loops are so small that trillions upon trillions of them would fit within the width of a single proton. Yet despite their minuscule size, they fundamentally change how we understand the universe's beginning. When matter collapses in this quantum geometric framework, something remarkable happens. As the density increases and space contracts, these quantum loops begin to resist further compression. It's not unlike trying to squeeze a sponge past a certain point. The discrete structure of space itself creates a kind of quantum pressure that pushes back against gravitational collapse. This resistance grows stronger as the density increases, until eventually the collapse stops entirely and rebounds into expansion. This quantum bounce creates what looks, from our perspective, exactly like a white hole. Matter doesn't emerge from nothing or from some mysterious external source. Instead, it flows outward from a previous phase of cosmic evolution, carrying with it the quantum imprint of that earlier universe. The uniformity we observe in the cosmic microwave background, the nearly perfect flatness of space, the precise ratios of matter to antimatter, All of these could be natural consequences of this quantum geometric process. But here's where things become truly fascinating. If our universe emerged from such a bounce, then every black hole in our cosmos might be undergoing the same process. Deep inside each black hole, as matter reaches the quantum geometric limit, it too would bounce. But where would that rebounding matter go? It can't return to our universe because nothing can escape from inside a black hole's event horizon. Instead, it would create its own pocket of expanding space-time, its own universe. This leads us to one of the most profound implications of the white hole hypothesis. Our universe might not be unique or isolated. It could be just one bubble in an infinite foam of interconnected realities, each one born from the quantum collapse of matter in another. Every black hole becomes a cosmic seed, a birthplace for new universes. Every white hole, including potentially our own Big Bang, represents the flowering of that seed into a full reality. The mathematical elegance of this picture is striking. In classical physics, black holes and white holes are perfect mirror images of each other, related by time reversal symmetry. But in quantum gravity, they become part of a dynamic process, two phases of the same underlying phenomenon. The black hole phase represents the compression and information processing stage, while the white hole phase represents the expansion and structure formation stage. This quantum geometric approach also addresses one of the most troubling aspects of traditional cosmology, the question of what came before the Big Bang. If our universe emerged from a white hole, then there was indeed a before, but it was causally disconnected from our current reality. The quantum bounce acts as a kind of information barrier, preserving some features of the previous universe while erasing others. Think about what this means for our understanding of time itself. In the traditional Big Bang model, time begins at the moment of the singularity, but in the white hole scenario, time is more like a river that flows from one universe to another. The quantum bounce represents a kind of temporal waterfall where the flow of time transitions from one cosmic epoch to another. Recent work by physicists like Carlo Rovelli and Francesca Vidotto has begun to map out what this transition might look like in detail. Their calculations suggest that the quantum bounce isn't instantaneous. Instead, it unfolds over a brief but finite period, during which the normal rules of spacetime are suspended and quantum geometric effects dominate. This transition phase, lasting perhaps a Planck time, represents the closest thing to a true beginning that physics can describe. But even this quantum beginning isn't absolute. The universe that collapsed to create our white hole had its own history, its own evolution, its own story. And that universe might have emerged from yet another quantum bounce, creating an infinite chain of cosmic rebirths stretching back through time without end. This raises profound questions about the nature of existence itself. If universes can emerge from quantum bounces, if black holes can birth new realities, then what we call creation becomes not a singular event, but an ongoing process. The universe isn't just expanding and evolving, it's reproducing, creating copies and variations of itself through the quantum geometric processes that govern extreme gravitational collapse. The implications extend beyond cosmology into the realm of information theory and consciousness. If our universe carries quantum imprints from a previous reality, then in some sense the past is never truly lost. Information that fell into black holes billions of years ago might be encoded in the fundamental structure of spacetime itself. The patterns we see in the cosmic microwave background, the distribution of galaxies, even the constants of physics might all be echoes of events that occurred in a universe that existed before our own. This connects to another fascinating aspect of white hole cosmology, the possibility that the laws of physics themselves might evolve. In the traditional view, the constants of nature are fixed and eternal. But if universes emerge from quantum bounces, then these constants might be subject to variation and selection. Universes that produce more black holes would create more offspring, while those that don't would be evolutionary dead ends. Over cosmic time, this could lead to a kind of natural selection for universes that are particularly good at forming black holes. Our universe, with its abundance of stars and galaxies, each containing supermassive black holes, might be the product of this cosmic evolutionary process. The fine-tuning we observe, the precise values of fundamental constants that allow for complex structures to form, might not be accidental, but the result of billions of cosmic generations of selection and refinement. The white hole hypothesis also offers a new perspective on the arrow of time. Why does time flow from past to future? Why do we remember yesterday but not tomorrow? In the quantum bounce scenario, the arrow of time is reset with each cosmic cycle. The white hole explosion creates a new temporal direction, a fresh start for causality and thermodynamics. This temporal resetting might explain why our universe appears to have such low entropy at its beginning. In the traditional Big Bang model, the early universe's low entropy is simply assumed, a fine-tuning problem that requires special initial conditions. But in the white hole scenario, the low entropy emerges naturally from the quantum geometric processes that govern the bounce. The quantum compression and expansion acts like a cosmic reset button, creating order from chaos and giving time its direction. As we contemplate these possibilities, we're forced to confront the limits of our current understanding. The white hole hypothesis pushes us to the very edge of what physics can describe, where quantum mechanics meets general relativity, where the discrete meets the continuous, where the finite meets the infinite. It's a realm where our usual intuitions about space and time break down, where the familiar becomes strange and the impossible becomes merely improbable. Yet despite these challenges, the hypothesis offers something that traditional cosmology struggles to provide: a complete picture of cosmic evolution that doesn't require arbitrary beginnings or unexplained fine-tuning. If our universe is indeed the interior of a white hole, then it represents not the birth of everything, but the continuation of something far grander and more mysterious than we ever imagined. Now that we've explored the profound implications of a white hole origin, we arrive at one of the most compelling questions in modern cosmology. Could the structures we observe today actually preserve the fingerprints of this explosive birth? The cosmic web we see around us, the vast network of galaxies, clusters, and supervoids, tells a story written in the language of gravity and time. In the Standard Model, these structures grew from tiny quantum fluctuations, stretched and amplified by inflation, into the seeds of everything we see today. But if our universe emerged from a white hole, that story changes dramatically. Picture the moment of emergence. Instead of a smooth, symmetric expansion from a singular point, we have a directional explosion from a bounded surface. Matter and energy don't just appear everywhere at once. They flow outward from a specific geometric structure, carrying with them the imprint of that original boundary. This changes everything about structure formation. In a white hole scenario, the initial conditions aren't set by random quantum noise, but by the specific geometry and dynamics of the explosion itself. The matter distribution wouldn't be perfectly uniform with tiny random fluctuations. Instead, it would carry systematic patterns, flows, preferred directions, and correlations that reflect the original ejection process. Consider what this means for galaxy formation. Instead of gravity slowly gathering matter from nearly uniform initial conditions, we might see preferential flows along specific directions, creating what cosmologists call bulk flows, large-scale motions of galaxy clusters that seem to stream in coordinated patterns across hundreds of millions of light-years. Remarkably, we do observe such bulk flows in the real universe. The Great Attractor is a gravitational anomaly that appears to be pulling our local group of galaxies, along with thousands of others, toward a region of space behind the Milky Way. Even more intriguingly, there's evidence for what astronomers call the dark flow, a mysterious bulk motion of galaxy clusters on scales so large that they shouldn't exist in standard cosmology. These observations have puzzled cosmologists for decades. In the standard model, the universe should look essentially the same in all directions once you average over sufficiently large scales, but the bulk flows suggest there are preferred directions, systematic motions that seem to violate this fundamental assumption. A white hole origin could naturally explain these features. If our universe emerged from a directional explosion, the initial velocity field of matter wouldn't be random. It would carry the signature of that original outflow. Regions of space that were ejected in similar directions would maintain correlated motions, creating the bulk flows we observe today. The implications go deeper than just velocities. The white hole's internal structure would also affect how matter was distributed initially. Unlike the nearly scale-invariant fluctuations predicted by inflation, a white hole might produce features with characteristic scales, preferred sizes and shapes that reflect the geometry of the original explosion. This could explain another puzzling observation. The cosmic web itself has a surprisingly filamentary structure. Galaxies aren't just randomly distributed, they're organized into vast sheets and filaments separated by enormous voids. While gravity can amplify initial fluctuations, the particular pattern we see, with its characteristic scales and void sizes, might be better explained by a directional origin than by random quantum noise. Even more intriguingly, some researchers have suggested that the alignment of large-scale structures might preserve information about the original white hole geometry. If matter was ejected preferentially along certain axes, those directions might still be visible today in the orientation of galaxy clusters and superclusters. The white hole scenario also offers a fresh perspective on dark matter. In standard cosmology, dark matter is assumed to have formed through thermal processes in the early universe, reaching equilibrium with the hot plasma and then freezing out as the universe cooled. But if the universe began with a violent explosion from a white hole, dark matter might have formed through entirely different mechanisms. Perhaps dark matter was directly ejected from the white hole, already in a non-thermal state. This could explain why dark matter seems to have such specific properties, why it interacts so weakly with ordinary matter, and why it has just the right abundance to dominate the universe's mass budget. Instead of being a coincidental byproduct of particle physics, dark matter might be a direct remnant of the white hole explosion. This non-thermal origin could also explain some of the puzzling small-scale properties of dark matter. Computer simulations based on standard cold dark matter theory predict that galaxies should be surrounded by many more small satellite galaxies than we actually observe. This missing satellites problem has led to increasingly exotic explanations, but a white hole origin might naturally produce dark matter with different clustering properties. The white hole framework also addresses one of cosmology's deepest mysteries: the arrow of time. Why does the universe evolve from order to disorder? Why does entropy increase? In the standard model, this is simply assumed. The universe began in a special, low entropy state, for reasons we don't understand. But if the universe emerged from a white hole, the arrow of time becomes a natural consequence of the explosion itself. The white hole represents a maximum entropy state in the parent universe, but when that matter explodes into a new spacetime, it begins with low entropy relative to the new space it can occupy. The subsequent increase in entropy is simply the universe expanding into the available phase space. This perspective also suggests that the fine-tuning problems that plague standard cosmology might be resolved. Why is the universe so remarkably flat? Why are the fundamental constants so precisely balanced? If our universe is the interior of a white hole connected to a parent universe, these properties might be inherited rather than coincidental. The parent universe would have had its own evolutionary history, its own processes of star formation and galaxy evolution. The matter that eventually formed our universe would have been processed through billions of years of cosmic evolution, potentially explaining why our physical constants seem so well suited for complexity and life. But perhaps the most profound implication is that structure formation in a white hole universe might be fundamentally different from what we expect. Instead of a bottom-up process where small structures merge to form larger ones, we might see top-down formation where large-scale flows and patterns existed from the beginning. This could explain why the largest structures in the universe, the cosmic web itself, seem to have formed earlier than expected. Observations of the early universe reveal that massive galaxy clusters and large-scale structures were already in place at times when they should still have been forming according to standard theory. As we continue to map the universe with ever greater precision, we're building a detailed picture of how matter is distributed on the largest scales. Future surveys will measure the positions and motions of billions of galaxies, allowing us to reconstruct the cosmic velocity field with unprecedented accuracy. If the universe did emerge from a white hole, these measurements might reveal the smoking gun, systematic patterns in the cosmic flow that point back to a common origin, frozen echoes of that primordial explosion still visible in the dance of galaxies across the cosmic web. The structure we see today isn't just a snapshot of the present, it's a fossil record of the universe's birth, carrying within it the memory of how everything began. And that memory might be telling us a story far stranger and more beautiful than we ever imagined. Looking at the extensive research on white holes and their potential connection to the Big Bang, we arrive at a fascinating crossroads where theoretical physics meets observational cosmology. The question of whether our universe emerged from a white hole represents one of the most profound challenges to our understanding of cosmic origins. The evidence we've explored reveals a compelling theoretical framework. White holes emerge naturally from the mathematics of general relativity as time-reversed black holes, creating regions where matter and energy can only flow outward. When we consider the observational puzzles that have long plagued standard Big Bang cosmology, the horizon problem, the flatness problem, and the mysterious uniformity of the cosmic microwave background, a white hole origin offers elegant solutions without requiring the exotic mechanisms of cosmic inflation. The mathematical consistency is particularly striking. In loop quantum gravity and Einstein-Cartan theory, quantum effects near the Planck scale can prevent the formation of true singularities, instead creating bounce scenarios where a collapsing universe transitions into an expanding one through what appears to be a white hole phase. This removes the troubling infinities that plague traditional Big Bang models while preserving the successful predictions of Big Bang nucleosynthesis. The observational hints are tantalizing. The anomalies in the cosmic microwave background, the cold spot, the unusual alignments at large angular scales, and the suppression of power at the larger scales all find natural explanations in white hole models. The universe's apparent emergence from a state of maximum compression, followed by explosive expansion, mirrors exactly what we would expect from a white hole event. However, significant challenges remain. The thermodynamic arrow of time presents a fundamental obstacle, as white holes would seem to violate the second law of thermodynamics by creating order from chaos. The instability of white hole solutions in classical general relativity means they would collapse almost instantaneously unless sustained by exotic matter or quantum effects we don't yet fully understand. The detectability question looms large. If white holes are inherently unstable and short-lived, direct observation becomes nearly impossible. We must rely on indirect signatures, unusual gravitational wave patterns, anomalous high-energy bursts, or subtle imprints in the cosmic background radiation. While some gamma-ray bursts and fast radio bursts remain unexplained, none yet clearly point to white hole origins. The integration with quantum gravity theories offers both promise and complexity. While loop quantum gravity naturally incorporates bounce scenarios that resemble white hole behavior, string theory struggles to accommodate stable white hole solutions. The full quantum treatment of these objects remains incomplete, leaving crucial questions about their formation, stability, and observable consequences unanswered. Perhaps most intriguingly, the white hole hypothesis offers a profound reframing of cosmic origins. Rather than emerging from nothing, our universe might represent a continuation, the explosive birth from a parent cosmos through quantum gravitational processes we're only beginning to understand. This connects to broader ideas about cosmic reproduction, multiverse theories, and the cyclical nature of cosmic evolution. The implications extend beyond cosmology into fundamental physics. If our universe emerged from a white hole, it could explain the observed matter-antimatter asymmetry, influence the formation of dark matter, and provide new insights into the nature of space-time itself. The early universe's departure from the thermal equilibrium, naturally explained in white hole scenarios, could have profound consequences for particle physics and the fundamental constants we observe. Looking toward the future, several observational pathways could provide crucial tests. The next generation of gravitational wave detectors, particularly space-based observatories like LISA, will probe the primordial gravitational wave background with unprecedented sensitivity. If our universe emerged from a white hole rather than through cosmic inflation, the gravitational wave signature should be distinctly different, potentially showing sharp features, directional biases, or unusual frequency distributions. Advanced cosmic microwave background observations will map temperature and polarization patterns with ever greater precision, potentially revealing the geometric signatures of a white hole origin. The search for unusual transient events continues, with automated sky surveys monitoring for the brief, intense bursts that might signal white hole formation or evaporation. The theoretical work continues as well. Researchers are developing more sophisticated models that incorporate quantum gravity effects, study the stability of white hole solutions, and explore the connections between black hole interiors and expanding universes. The mathematics of shockwave cosmology, torsion-based gravity, and quantum bounce scenarios all contribute pieces to this cosmic puzzle. In weighing the evidence, we must acknowledge that the white hole hypothesis remains speculative. It offers compelling theoretical advantages and addresses genuine problems in standard cosmology, but it lacks the observational confirmation that would elevate it from possibility to accepted theory. The challenges of thermodynamics, stability, and quantum consistency represent significant hurdles that future research must overcome. Yet the very existence of these ideas demonstrates the vitality of cosmological thinking. Science advances not just by confirming existing theories, but by questioning fundamental assumptions and exploring alternative possibilities. The white hole hypothesis, whether ultimately correct or not, has already enriched our understanding of spacetime, causality, and cosmic evolution. The question of whether the Big Bang was a white hole touches on the deepest mysteries of existence. It challenges us to think beyond conventional boundaries, to consider that our universe might be connected to realms we cannot directly observe, and to embrace the possibility that the story of cosmic origins is far stranger and more beautiful than we ever imagined. As we stand at the threshold of a new era in observational cosmology, With gravitational wave astronomy, precision cosmic surveys, and advancing theoretical frameworks, we may finally be approaching the tools needed to test these profound ideas. The universe itself will be our laboratory, and the answer to whether we emerged from a white hole may be written in the very fabric of space and time, waiting for us to learn how to read it. In the end, the white hole hypothesis represents more than just an alternative cosmological model. It embodies our endless quest to understand our place in the cosmos and the fundamental nature of reality itself. Whether our universe began with a bang or emerged from a white hole, the journey of discovery continues, guided by observation, theory, and the insatiable human desire to comprehend the magnificent mystery of existence. Now, this is where things get deliciously complex. You see, the white hole hypothesis doesn't just challenge our understanding of cosmic origins, it forces us to completely reimagine the very fabric of reality itself. And I do hope you're still comfortably settled in, because we're about to embark on the most intricate part of our journey, where mathematics meets mystery and where the impossible becomes tantalizingly plausible. Let's begin with something that might sound rather abstract but is actually quite beautiful in its implications. If the Big Bang was indeed a white hole event, then we need to ask ourselves a fundamental question. What exactly is time? Not the kind of time you check on your phone, but the deep, structural time that governs the universe itself. You see, in a white hole scenario, time doesn't simply begin at T equals 0. Instead, it flows like a river with multiple tributaries, some flowing forward, some perhaps flowing backward, all converging at that singular moment we call the Big Bang. Imagine, if you will, standing at the edge of a cosmic waterfall. Everything you know, everything you've ever experienced, comes rushing towards you from that single point of origin. But here's the remarkable thing about white holes. They don't just expel matter and energy randomly. They do so according to precise mathematical rules, following what physicists call the geodesic equations of spacetime. Every particle, every photon, every quantum of energy that emerged from this primordial white hole followed a predetermined path through the curved geometry of spacetime. This brings us to one of the most profound implications of the white hole hypothesis: the question of determinism versus randomness in cosmic evolution. In traditional Big Bang cosmology, we often invoke quantum fluctuations to explain the slight irregularities that eventually became galaxies and stars. But if our universe emerged from a white hole, these irregularities might not be random at all. They could be the geometric echoes of whatever collapsed into the parent black hole in some previous cosmic epoch. Think about it this way. Every galaxy you see in the night sky, every star that twinkles overhead, might be the descendant of structures that existed in a universe that came before ours. The white hole didn't create these patterns from nothing. It preserved them, transformed them, and expelled them into our expanding cosmos. It's rather like a cosmic archaeological record, written not in stone, but in the very distribution of matter and energy throughout space. But here's where the mathematics becomes truly extraordinary. White holes, as solutions to Einstein's field equations, exist in what physicists call the maximal extension of spacetime. This isn't just a fancy way of saying they're big. It means they're connected to regions of spacetime that we can't normally access. In the complete mathematical picture, a white hole is eternally connected to a black hole through what we might call the Einstein-Rosen bridge, that hypothetical tunnel through spacetime that science fiction has made famous as a wormhole. Now, I know what you're thinking. If there's a tunnel connecting our universe to some other region of spacetime, shouldn't we be able to detect it somehow? Well, here's the beautiful irony. The connection exists, but it's not traversable. The throat of the wormhole, that narrow region linking the black hole and white hole, pinches off faster than light can travel through it. It's like having a door that closes before you can walk through it, no matter how quickly you try to move. This geometric constraint has profound implications for information and causality. If our universe emerged from a white hole, then technically it's causally connected to whatever fell into the parent black hole. But practically speaking, no information can flow between these regions. We are cosmically isolated, cut off from our origins by the very geometry of space-time itself. It's a kind of cosmic amnesia built into the structure of reality. Let's delve deeper into the quantum mechanical aspects of this scenario. In quantum field theory, the vacuum of space isn't truly empty. It's filled with virtual particles that pop in and out of existence, creating what physicists call zero-point energy. Now, in the extreme environment near a white hole horizon, these quantum fluctuations become amplified in fascinating ways. The intense curvature of space-time can turn virtual particles into real ones, a process similar to what Stephen Hawking described for black holes, but running in reverse. This quantum amplification might explain some of the most puzzling observations in cosmology. For instance, the cosmic microwave background radiation, that faint afterglow of the Big Bang, shows tiny temperature variations that seem almost too perfect to be random. If these fluctuations were amplified from quantum noise near a white hole horizon, they might naturally exhibit the statistical properties we observe without requiring fine-tuning of inflation parameters. But perhaps the most intriguing aspect of the white hole hypothesis is how it handles the arrow of time. In our everyday experience, time flows in one direction, from past to future, from order to disorder, from low entropy to high entropy. But near a white hole, this arrow becomes ambiguous. The white hole itself represents a region where entropy decreases, where disorder becomes order, where the scattered remnants of a collapsed universe reorganize themselves into the structured cosmos we inhabit. This creates what physicists call a thermodynamic paradox. How can a region of spacetime violate the second law of thermodynamics, which states that entropy must always increase? The answer lies in the global structure of spacetime itself. If we consider the entire black hole-white hole system, entropy is conserved overall. What decreases in the white hole region is precisely balanced by what increased in the black hole region. It's a cosmic accounting system that maintains the fundamental laws of physics while allowing for apparently impossible local violations. Now let's consider the observational consequences of this scenario. If our universe emerged from a white hole, we might expect to see certain signatures in the cosmic microwave background that differ from standard inflationary predictions. For instance, the polarization patterns of the background radiation might show subtle asymmetries that reflect the geometry of the white hole horizon. These would be incredibly difficult to detect with current technology, but future space missions might be sensitive enough to pick up these faint signals. There's also the question of what happened to the wormhole connection after the Big Bang. In most models, the Einstein-Rosen bridge is unstable and collapses almost immediately. But some theoretical work suggests that quantum effects might stabilize it temporarily, creating a brief window during which information could flow between the universes. This information transfer wouldn't violate causality because it would occur before the light cones of the two regions separate completely. If such information transfer occurred, it might have influenced the initial conditions of our universe in subtle ways. The distribution of dark matter, the precise values of fundamental constants, even the quantum fluctuations that seeded structure formation, all might bear the imprint of this primordial information exchange. It's as if our universe inherited a genetic code from its parent, encoded not in DNA, but in the very fabric of space-time. This brings us to one of the most profound questions in all of cosmology. Why does our universe seem so perfectly tuned for the existence of stars, planets, and life? The traditional answer invokes either divine intervention or the anthropic principle, the idea that we observe a life-friendly universe simply because we're here to observe it. But the white hole hypothesis offers a third possibility. Our universe inherited its life-friendly properties from a parent universe that had already evolved the conditions necessary for complexity and life. In this view, the fine-tuning of physical constants isn't a miracle or a selection effect, it's an inheritance. Universes that produce black holes naturally give birth to white hole universes with similar properties. Over countless generations of cosmic reproduction, the multiverse would evolve toward configurations that maximize the production of black holes, and hence the creation of new universes. It's a form of cosmic natural selection, operating not on biological organisms, but on entire realities. The mathematics of this process is still being worked out, but the basic idea is elegant in its simplicity. Each black hole that forms in our universe might give birth to a new universe through a white hole explosion. The new universe would inherit properties similar to ours, but with slight variations introduced by quantum fluctuations during the collapse and bounce process. Over time, this would lead to a branching tree of universes, each one slightly different from its parent, but all sharing a common cosmic ancestry. This scenario also provides a natural resolution to the horizon problem, one of the classic puzzles of Big Bang cosmology. How did regions of space that were never in causal contact end up with the same temperature and density? In the white hole model, these regions were in contact in the parent universe before the collapse that created the black hole. The apparent fine-tuning of initial conditions isn't fine-tuning at all. It's the result of causal processes that occurred before our universe began. But here's where the story takes an even more fascinating turn. If black holes in our universe are giving birth to new universes, then we might be able to detect indirect evidence of this process. When a massive star collapses to form a black hole, the information about its internal structure might be preserved and passed on to the daughter universe. This could create correlations between the properties of black holes in our universe and the initial conditions of the universes they spawn. Of course, we can't directly observe these daughter universes, but we might be able to infer their existence through subtle effects on the black holes themselves. For instance, if information is being transferred from black holes to white holes, it might affect the Hawking radiation that black holes emit. Instead of being completely thermal and random, the radiation might carry encoded information about the daughter universe's properties. This idea pushes us to the very edge of what's physically possible and observationally testable. We're talking about using the most sensitive instruments ever built to detect the faintest possible signals from processes that may be occurring in regions of space-time we can never directly access. It's like trying to eavesdrop on a conversation happening in another dimension, using only the shadows it casts in our own reality. Yet this is precisely the kind of challenge that makes physics so thrilling. We're not just asking what happened at the beginning of time. We're asking whether time itself has a beginning, whether our universe is unique or one of countless others, whether the laws of physics as we know them are fundamental or emergent properties of a deeper, more complex reality. As we contemplate these possibilities, drifting gently through the cosmos of ideas, we find ourselves at a remarkable juncture in human understanding. The white hole hypothesis doesn't just offer an alternative to the Big Bang, it suggests that our entire conception of cosmic origins might be fundamentally incomplete. We may be living not in the first universe, but in the latest chapter of an ongoing story that stretches back through countless generations of cosmic evolution. And so, as we near the end of our journey through this labyrinth of space, time, and possibility, we're left with a profound sense of wonder. Whether or not the Big Bang was actually a white hole, The very fact that we can contemplate such ideas speaks to the extraordinary power of human imagination and mathematical reasoning. We've taken equations written on paper and used them to peer into the deepest mysteries of existence itself. The universe may be vast and ancient and strange beyond our wildest dreams, but it's also comprehensible, at least in part, to curious minds willing to follow the mathematics wherever it leads. And perhaps that's the most remarkable thing of all, that in a cosmos born from a white hole, or a quantum fluctuation, or some process we haven't yet imagined, there emerged beings capable of wondering about their own origins, of asking the deepest questions, and of finding, in the very act of questioning, a kind of answer to the mystery of existence itself. So we've travelled through the labyrinth of possibilities, from quantum bounces to cosmic cycles, from white holes to multiverses, and now we find ourselves at the edge of the deepest question of all. What does it mean to exist in a universe that may have no true beginning? If the Big Bang was indeed a white hole, then our story becomes radically different. We are not the products of creation from nothing, but the children of transformation, the inheritors of a cosmic lineage that stretches back through cycles of collapse and rebirth, death and resurrection, across dimensions we cannot see, and through times we cannot fathom. This perspective reshapes everything. The atoms in your body, forged in the hearts of stars, may themselves be the descendants of atoms that lived and died in universes before ours. The light from distant galaxies, travelling billions of years to reach your eyes, may carry within it the memories of spaces that existed before our space began. The very fabric of space-time, which we think of as the stage upon which all drama unfolds, may be just one act in an infinite play. The white hole hypothesis suggests that our universe is not a closed book with a clear beginning and an uncertain end, but rather a single page in an endless library. Each black hole that forms in our cosmos may be the seed of a new universe, a new chapter in the ongoing story of existence. Each collapse becomes a birth, each ending a beginning. The universe does not create itself from nothing, but transforms itself through everything. This vision carries profound implications for how we understand our place in the cosmic order. If universes reproduce through black holes, then the physical constants that govern our reality, the forces that hold atoms together, the expansion rate that determines whether stars can form, all of these may be the result of a kind of cosmic natural selection. Universes that produce more black holes leave more offspring, while those that fail to do so fade into extinction. Our universe, with its delicate balance of forces that allows for complexity, life, and consciousness, may be the product of billions of years of cosmic evolution, fine-tuned not by design, but by the simple process of reproduction and inheritance. We exist not because we were specially created, but because we are the descendants of universes that were good at making more universes. The white hole origin also suggests that information is never truly lost, that the patterns and structures of existence persist across cosmic generations. The quantum information that falls into black holes may not disappear forever, but may be transformed and reborn in new universes, carrying forward the accumulated experience of cosmic evolution. If this is true, then consciousness itself may be part of this grand recycling process. The thoughts you're thinking right now, the awareness that contemplates these possibilities, may be built from information that has travelled through multiple universes, refined and evolved through countless cycles of cosmic death and rebirth. The horizon problem, the flatness problem, the uniformity we observe in the cosmic microwave background, all of these may be natural consequences of emerging from a white hole that processed and organised the chaotic remnants of a previous universe. What we see as the fine-tuning of cosmic parameters may simply be the result of a universe that has had time to get things right, to evolve toward conditions that support complexity and life. But perhaps the most profound implication is temporal. If our universe emerged from a white hole, then time itself may be more fluid and mysterious than we imagine. The white hole represents a boundary beyond which causality breaks down, where the normal rules of before and after lose their meaning. Our universe may be connected to its predecessors not through time as we understand it, but through deeper structures of space-time that transcend our ordinary experience. This suggests that the ultimate nature of reality may be far stranger and more wonderful than even our most ambitious theories propose. We may be living not in a universe, but in a multiverse, not in time, but in something that contains time, not in space, but in something that gives birth to space. The search for evidence of this cosmic ancestry continues. In the patterns of the cosmic microwave background, in the distribution of galaxies, in the behavior of black holes, in the detection of gravitational waves, we may find the fingerprints of our universe's birth from a white hole. Each new observation brings us closer to understanding whether we are truly the first of our kind or the latest in an ancient lineage. And if we are indeed the products of a white hole, then we are also the progenitors of future universes. The black holes that form in our cosmos may be the wombs of new realities, new experiments in the physics of existence. Through us, through our universe, the cosmos continues its eternal process of self-creation and self-discovery. In this vision, the Big Bang becomes not the beginning of everything, but a moment of transition, a cosmic inhale followed by the exhale of expansion. We are not witnesses to creation, but participants in transformation, not the end point of evolution, but a way station in a journey that has no beginning and no end. The white hole hypothesis reminds us that the universe is not a problem to be solved, but a mystery to be lived. We are part of something vast and ongoing, something that transcends our individual existence, while simultaneously giving it meaning. We are the universe becoming aware of itself, asking questions about its own nature, contemplating its own origins. Whether the Big Bang was a white hole or something else entirely, the questions it raises about the nature of existence, the meaning of time, the possibility of infinite creativity in the cosmos. These questions touch the very heart of what it means to be conscious beings in an apparently unconscious universe. As we stand at the threshold of new discoveries, as our instruments become more sensitive and our theories more sophisticated, we may finally begin to answer the question that has haunted human consciousness since we first looked up at the stars and wondered where we came from. The answer, when it comes, may be stranger and more beautiful than anything we have yet imagined. Until then, we remain explorers in the infinite mystery of existence, children of the cosmos seeking to understand our cosmic parentage, inheritors of a universe that may itself be the heir to universes beyond counting. And in that seeking, in that wondering, in that eternal human quest to comprehend our place in the grand scheme of things, we honour the profound mystery that gave birth to us all. The story continues, and we are both its authors and its characters, writing the next chapter in the endless book of cosmic evolution.